Okay, good afternoon, everybody. Kanal Sopanya, Swandara, Kinsin, and others. I don't know, a lot of students, but I don't have to mention everybody's name. Guys, I hope you are doing well. Let's start. Okay, we're going to have two short sessions. Maybe each one will be around 35 seconds. I think that much is enough for online classes. Last time we were talking about matrix operations, right? Actually, the definition, dimensions, or the size of the matrices when they are equal to each other. How do we add two matrices and how do we subtract one matrix from another one? And scalar multiplication and one more problem. And I think I stopped here. Okay, that's what I remember. So today is 22nd of June, I think, is it? Yes, today is Thursday, this 23rd. Okay, now let's continue from here, okay? 35 minutes after they'll have 15-minute break, then we'll have our second session. That's it for today. Okay. So now, guys, from now on, we are going to actually express our system of linear equations as the matrix and the vector and the vector. See here, actually, you're familiar with this notation just one more time, since now we are studying about matrices. That's why this example is given here. See here, if you look at this system of linear equations, x plus 3y minus 2 is equals 5, 3x plus 5y plus 6 equals 7, 2x plus 4y plus 3 equals 8, right? See here, how did it form our augmented matrix? First, we just wrote our coefficient matrix, and next to it we have just augmented the the constant matrix or the constant term matrix. Okay, so at that time, if I just separate this, here we have 1 3 negative 2 3 5 6, and see here's just coefficient matrix. Here we have x y z. If you multiply these matrices together, right, actually you will get the system of linear equations. So if you just label this thing by a, this unknown, that x, on the right hand side we have the constant vector, that is b. Actually, this a times x equals b, it represents the system of linear equations where we have n variables and n coefficients. Okay, it's just example. Actually, later we'll focus on this. That's really simple but important representation in linear algebra. Okay, theorem 3.1. Now we will start with very simple but important, because we're going to use this notation in proving a lot of few theorems. Suppose that we are given m by n matrix A. Okay, and actually when you just say that, immediately you have to imagine that we're talking about this kind of matrix. Right here we have A, and here we have these elements, and it has how many? It has m rows and n columns. So that means that here we have A11 and dot dot A1n. And also here we have A21 dot dot, and here we have AM1. And the last one is AMN. Okay, we're talking about this kind of matrix. Now, and also I'm just going to label by this E sub I 1 by m matrix. Okay, what do we mean by this? This E sub I, it is a standard unit vector. That means that it has n components, and it is i's i's component is 0. So here we have 0, 0, dot, dot, and here we have 1, dot, dot, 0. Now, what is I? This one is i's column. All right. And the second one is with ij. For here, we are just labeling or denoting n by 1 standard unit vector. So this our ij it is a column vector. Here we have 0, 0, dot, dot, and here we have 1, dot, dot, here we have 0. And where is this one? This is in J's column. Okay, this one is i's. Sorry, this one is i's column, and this one is J's row. Okay, so that is actually it's going to be the science of coding. This kind of notations are really important. Now, this theorem is saying that after introducing actually these standard unit vectors, if you multiply this A by from left by EI, it gives us the ith row of A. And if you multiply this by EJ from right, it gives us the j's column of A. Just to understand, again, I suggest you to just give one simple example to understand. And suppose that, for example, if our A, let's say that these matrices is A and the B and the C and D, or A, B, C, D, it doesn't matter. Okay. So now if you just multiply this by this vector, let's say if you multiply this by A, C, B, D, right? And from left, right, E, I'm going to multiply this by this. Let's say this 1, 0. That means that actually here the 1 is the first component is not equal to 1, right? So I'm expecting that this product should give us the first column of this matrix, right? So if you do so, actually, once again, check its dimensions. This one is 1 by 2, and this matrix is 2 by 2. The resulting matrix will be, what is it? 1 by 2. That means 1 row and 2 columns. So it will be 1 row and 2 columns. We will have something like this. Something like this. It must give us the first row. It says ith row of A. So now if you multiply this A times 1, A, B times 0, 0, so that is A. Multiplies by the second column, 1 times C, C, 0 times C, that is, what is it? It is C. Let's see here, AC is the first row of this one. Now if you multiply the same thing by 0, 1, and here we have AC and BD, it gives us the second row. 0 times A, 0, 1 times C, 0 times A, 0, 1 times B, it is B. The second one, 0 times C, 0, 1 times C, it is D. And what is BD? It is just the second column, the row, sorry. This one is the first row, and this one is the second row of the given matrix. Okay, that's why if you're given a standard vector, unit vector, I mean, row vector or what is that, column vector, depending on the situation here. If you multiply A by EI from left, it gives us the ith row. And if you multiply A by from right by EJ, it gives us the j's column of A. Okay, and of course, then just use them in example, you'll understand more. Now, next thing is, let's talk about what is it, partition matrices. Okay, so one way, actually, the reason why we need to partition matrices is sometimes, if you're given very big matrices, inside the matrices, we may have a lot of zeros, or maybe we have some kind of, what is it, ones in the diagonal. Okay, at the time, if you just partition this, it really gives you a lot of convenience to how to say, when you're multiplying two matrices together or adding two matrices together, especially in multiplication, it will be really convenient. So it will be convenient to regard a matrix as being composed of a number of smaller submatrices. By introducing vertical and horizontal lines into a matrix, we can partition it into blocks. Let's see here, if we are given actually this matrix, right, the big matrix. Now, if I just introduce two lines here, right, and just label at the top 1 0 0 0 0 1 0 0 0 1. What is it? It's our identity matrix. At the bottom 0 0 0 0 0 0. That's just a zero matrix. That's why it is O. But this 2 1 1 3 is any arbitrary matrix. It is 3 by 2. That's B, and at the bottom also C. So in simply, we can just partition this matrix in this way. So as see here, if I'm multiplying this by another matrix, if it is defined at the time, when I'm multiplying this zero part, right? Just you can write this zero. An identity matrix, and also we know that if you multiply any matrix, it is defined A times I or I times A, that's just equal to A. We don't have to carry out these operations. Okay, another one is matrix column representation of a product. Okay, that's also another way of, what is it, computing matrix. So suppose that we are given matrix A, whose dimensions are m by n and b n by r. And especially because you're going to multiply, that's why these numbers must be the same. Otherwise, it's not defined. Now, if we just partition B, is column wise, just for example, the first column of B, because matrix means that it has rows and columns. The first column, let me just label this by B1, the second column, B2, and B3, B4, B5, dot, 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 BR. It has R columns. And we are multiplying this by A. So what will be the result? The result will be A times B1, A times B2, A times BR. These are not the numbers. If you just check this one, for example, here, what is A? A is M by N matrix, right? And how about this one? It has only one column, but how many rows? N. So that is N by 1 matrix. So the results of this multiplication of the product will be an N, right? It will be M by 1. So H1 is, this one is M by 1 matrix. This one is M by 1, M by 1. H1 is M by 1 matrix. That's why here we have R columns, right? Each column has M rows. Example 9, using the matrix column representation, compute AB for the following matrices. Sam 9, do you hear me well? Sam 9, Sakap? So you're not here. Miss San, are you here? Okay. Hangli, do you hear me well?
Yes, sir.
All right, thank you very much. Because there's one person here. That's good news. Okay. Let's continue. Example 9, using the matrix column representation, compute AB for the following matrices. So the solution, so how are we going to do this? First, if you just partition this, see here, this our matrix A, right? The partitions will be B1, the first column of B, and B2, the second column, right? To do this one, first, I need to multiply this A by B1. So A is, what is it? 1, 3, 2, 5, 1, negative 2. And how about B1, the first column of B, that is 3, 1, and 5. So that is much faster, right? Here we have 1 times 3. We know that actually 3 by 2, and it's for 2 by 3, and 3 by 1. It will be 2 by 1 matrix. Here, the result will be something like this. Okay, so the first one is the first row by the first column, 1 times 3, 3, 2 times 1, 2, it is 5, 1 times 5, it is 5, so that's equal to 10. And now we should multiply the second row by the first column. Actually, we have only one column here. 3 times 3, 9, 5 times 1, it is 5, it is 14, 14 minus 10, that's equal to, what is it, 4. That's the first column of this product. And how about if you multiply A by B2, here we have 1, 3, and 2, 5, and 1, negative 2. And here we have 0, minus 4, and 3, right? So that is equal to, again, it will be 2 by 1 matrix. 0 times 1, 0, 2 times negative 4, it is negative 8, and there's 3, so that is negative 5. 3 times 0, 0, 5 times negative 4, negative 20, negative 6, negative 26. So now we can just write the result, right? So what is AB? The first result, that is 10 and 4. The second result, negative 5 and negative 26. So that is the product of these matrices. Okay. So now you may wonder, guys, because we know how to actually multiply through the matrices. Do we have to do this? Actually, these things are really important in, how to say, not only in calculation, if you're writing some kind of algorithm or program, right, or proving something, at the time this will be important, not only for direct calculation. By just direct calculation, we are just, what is it, verifying that it works or it agrees with what we are saying. Another one is, what is it, row matrix representation. The first one was matrix column, right? First it is matrix, we are multiplying matrix by columns. But here, now we are going to do our partitioning in a bit different way. How about if we partition the rows of A, or the rows of matrix A into rows? Let's say we label the first row by capital A1, the second row by A2, and dot, 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 nth row by AM. Okay, and how about B? We are not changing B. So now if you carry out this product, A times B, So what is A? It's partition A1, A2, A3, AM times we are multiplying this by B. So this product will be equal to A1 times B, A2 times B, AN times B. So does it work? Actually here, since A is M by N matrix, right? For example, let's A1 and B. Now, what is the dimension of A1? It is a row, right? It has one row. And how many columns does it have? It has N columns. How about B? B is N by R matrix. So these numbers are the same. So the result of this product will be, what is it? 1 by R. Let's see here, each one is 1 by R, 1 by R. Each one is the row. So using the row matrix representation, compute AB for the following matrices. Again, here we are not actually, even if I ask in the quiz, for example, do it in this way, I'm not going to test your multiplication skill. Do you know this method or not? That's what we want to see. So it says that, what is it? Using the row matrix representation. So that means that this A, right? I can just write it as A1 and the A2. What is A1? The first row of A, and A2 is the second row of A. At that time, actually, to multiply this one, first I need to multiply A1 by B. What is A1? A1 is 1, 2, 1. And how about our B? B is 3, 0, 1 minus 4, and 5, it is 3. As see here, this one is, what is it? It is 1 by 3. This one is 3 by 2. The resulting matrix will be 1 by 2. So here we will have something like this, right? Two elements here. So now if you just carry over this, the first row by the first column, 1 times 3, 3, 2 times 1, it is 2, 1 times 5, 5, 5 plus is 7, 7 plus 3, it is 10. The second column, 1 times 0, 0, 2 times negative 4, negative 8 plus 3, it is negative 5. And how about A2 times B? A2 is the second row of matrix A, that is 3 and 5 and negative 2, right? And here we have matrix B, 3, 0, 1, negative 4, and 5 and 3. So this thing is equal to, again, we'll have 1 by 2 matrix. 3 times 3, 9. 5 times 1, 5. It is 14. 14 and minus 10, that is 4. The second column, 3 times 0, 0. 5 times negative 4, negative 20. Negative 6, it is negative 26. So now what will be this product? Let me just write at the top. The product, right, is A times B will be the first row, 10, negative 5. The second row, it is 4 and the negative 26. Next, okay, first, what is it? Matrix, column, row matrix. Now, how about column, row representation of a matrix? Okay, the column, row representation, again, in similar way, from the name, as the name suggests, right, column. So we have to partition the columns of A as A1, A2, AM. These are the columns of A. And let's also partition the rows of B by B1, B2, and Bm. At the time, if you just multiply these two matrices together, A times B, what is A? It is partitioned as, or column-wise, A1, A2, dot, dot, AN, because it has n columns. And how about B? B1, B2, dot, dot, Bn, it has B rows, right? So because these n's, they are the same, that's why this multiplication is defined. What will be the resulting matrix dimension? It will be M by R. So see here, if I multiply A1 times B1, A2 times B2, right? Dot, actually, it looks like dot product, but here we are multiplying again matrices, not a dot product. It's a bit different because when you're writing, you should be careful. So there's A1, B1, A2, B2, A and Bn. Actually, what is the dimension of this matrix? The dimension is M by N. And the dimension of each matrix is M by N. Also, this one is M by N. That's why if you just add how many matrices together and M by N matrices together, also the result will be M by N matrix. Example, what is it? Well, here we have two actually names. So here in this multiplication, what is it? It is row column representation of the product. Each element here, this AI, BI, it is called outer product. And later we're going to use this, okay, as outer product. That's the outer product of this, what is it, expansion. And how about AB, A1, B1 plus A2, B2 plus A and BM? It is outer product expansion of AB, the product AB. Okay, these are just algebraic, what is it? Terms that we have to know. Compute the outer product expansion of AB for the following matrices. How do we do that? Again, if I just actually, what is it, partition in this way, right? And also this B partition here like this. At the time here we'll have A1 will be 2, 0, and A2 is 3, 1, and A3 will be 1, 7. Right. And how about B? So B1, so since it is row, let's use capital letter. B1 is 9, 0. B2 is the second row, 1, 4. And B3 is 2, 3. Okay. So now the outer production, outer product expansion of this product will be, we know that that's equal to A times B, A1, B1 plus A2, B2 plus A3 and the B3, right? So that is the outer product of this expansion. So now we just carry over or evaluate each product. After that, we just put them. That's it. That's what we are expected here to do, to show here. Because in the question it says that compute the outer product expansions of AB for the following matrices. Let's start from the first one. What is A1, B1? What is A1? A1 is 2, 0, and B1 is 9, 0. I know that the result will be, actually this one is 2 by 3, and this one is 3 by 2, right? The resultant matrix will be of dimension 2 by 2. And I'll see here, what is easy thing here is you're just multiplying each element by each element, right? 2 times 9, it is 18, and 2 times 0, it is 0, and the second column, right? The second row, 0 times 9, it is 0, 0 times 0, it is 0. So that is the first one. In a similar way, how about A2 and B2? A2 is 3, 1, so that is 3, 1. And B2 is 1, 4, so that is 1 and 4. The result will be 2 by 2 matrix. 3 times 1, it is 3. 3 times 4, it is 12. 1 times 1, it is 1. 1 times 4, it is 4. Right. So we need to calculate 2 more. No, only 1 more, right? So the last one is A3 and the B3. A3 is 1, 7. It is 1 and 7. How about B3? B3 is 2, 3. It is 2, 3. So the result will be 1 times 2, it is 2. 1 times 3, it is 3. 7 times 2, it is 14. 7 times 3, 21. Okay. So now I can just write the outer product expansion of this AB. What is A1, B1? 18, 0, 0, 18, 0, 0, 0, right? Plus the second one, it is 3, 12, 1, 4, 3, 12, 1, 4. And the last one is 2, 3, 2, 3, and the 14, 21. So that is the outer product expansion of this AB. And of course, after that, if you just add them, okay, you can get the product of this matrix. And I think computers actually just use this method to evaluate 2 matrices. Question 12. Example 12. Consider the matrices A and B given below. Okay. So now suppose that we have to multiply or we have to partition this. What are we going to do here is first, again, if I just introduce some vertical and horizontal lines, we can just partition them in this way. Why? Because if you notice here, A, right at the top left corner, that top corner, we have identity matrix. At the bottom, 0, 0, 0. And how about B? Actually, we have arbitrary matrix here, but at the bottom, 1, 0, 0, 1, that is an identity matrix. 0, 0, 0, 0 is a 0, and blah, blah, right? Now, if you just actually write this as like blocks, each block is a matrix. At the time, here the first one will be A11, A12, A21, A22. Because A, right, we have four blocks here or four partition matrices, which actually consists of A. And how about B? We will have six, right? B11, B12, B13, and B21, and B22, B32. And we know these matrices, A11 is identity matrix, A21 is zero matrix, right? And here we have B21 identity matrix, B22 is, what is it? Zero matrix, right? So now after this, we just say that A and B are said to be partitions conformably for block multiplication. Why? Because just simply we can multiply this A by B. Usually, for example, how do you multiply this, right? If you want to multiply A by B, you multiply actually the first row by the first column, second column, and third column. It gives us the entries of the top, right? And how about the second row, the second column multiplied by the first column, and the second column, the third column? It gives us, the elements in the second row. For example, if you just multiply, let's say, we know that if you multiply this A by B, and this one is 2 by 2 matrix, this one is 2 by 3, right? And 2 is the same, so it will be 2 by 3. So we'll have something like this: 1, 2, 3, and 1, 2, 3, right? So now if I just take this one, for example, what is this element? Okay, this element will be, let me just write here. So it will be A and B, the product, right? What is it? Second row and second column. So it will be second row and second column. To do this one, I need to multiply the second row of A, right? That is, second row is A11 and A22, right? By the second column of this matrix. So that is, second column is B12 and B22. So if you multiply this, what is it? Here we have A11 times B12 plus A22 and B22. If you check this, for example, A11, what is A11? A11 is 3 by 3 matrix, right? There's 3 by 3. How about A12? B12, B12, it is 3 by 2 matrix. So see here, it is defined here. That's why we are saying that partition conformably for block multiplication. A22, it is 2 by 2. This one is 2 by 2. And how about B22? Also B22 is 2 by 2. Actually, it's a zero matrix. Also, this multiplication is defined. So when you're actually blocking or partition matrix, you need to pay attention to this. Is it partition conformably for block multiplication or not? Otherwise, it gives you unexpected results. Okay. Now let's talk about matrix powers. How many minutes? Okay, we have 10 more minutes. After that, we'll have break. When you studied real numbers, the powers of A is defined as what? So if you just multiply A by itself n times in a compact form, in a very short form, you can just write it as A to the power of n. So this n is called power, right? And also for matrices, the same thing can be defined. If matrix A is multiplied by itself A times, at the time, actually, we can just write it as A to the power of k, or A to the power of k is defined as A is multiplied by itself n times. And also by convention, actually, A to the power of 0, actually in real numbers, we know that A to the power of 0 is 1, right? In matrices, we just define it as A to the power of 0 is defined as what? The identity matrix. Okay, and also about the definition, we can prove this, but now just take it as a fact. So if A is a squared matrix, that means that the number of rows is equal to the number of columns, and R and S are non-negative integers. So that means they are maybe 1, 2, 3, 4, simple. They are natural numbers or counting numbers. Then these properties hold. A to the power of R, A to the power of S, simply like real numbers, is equal to A to the power of R plus S. And also a to the power of r to the power of s, that's equal to a to the power of rs. And also proof is very simple. Using the definition, we can prove this because a to the power of r, what does it mean? It means that a is multiplied by itself r times. And how about a to the power of s? That means that a is multiplied by itself s times. Now, again, how many a's do we have here? R plus s, right? Again, using definition, we can write it as a to the power of r plus s. Consider the following matrices. Okay, the first one is A, 1, 1, 1, 1, and B, for example, B is 0, -1, B, 1. And consider means that maybe we can multiply each other or we can evaluate the powers of these matrices. Okay, now for example, let's say what is a to the power of 10? How do you multiply this? So let me just label this one as A and this one a question B for A, right? If you evaluate, for example, a squared, what is it? Here we have 1, 1, 1, 1 times, and here we have 1, 1, 1, 1. And it's right here, 1 here. Doesn't look nice. Okay, so if you evaluate this, what is it? 1 times 1 plus 1 times 1, it is 2. 1 times 1, again, it is 2. Also, this is 2. Also, that is 2, right? For example, so what do we have here? Let's see here, 2, 2, 2, 2. That is just a common factor. I can just write it as 2 times 1, 1, 1, 1. And what is 1, 1, 1? It's our original matrix. That's equal to 2 times a. So this a squared is equal to 2 times a. Now, how about this a cubed? By definition, I can write it as a squared times a. Right? Now, what is a squared? We have just evaluated. That's equal to 2 times a times a. So it is 2 times a squared. And what is a squared again? It is 2 times a. So that's equal to 2 times a. So now we can write it as 2 squared a, right? Now I think we see the pattern, right? In a similar way, what will be a to the power of 4? A to the power of 4 will be a to the power of 3 times a. So now from here we can get this result. Then nth power of this matrix will be equal to 2 to the power of n minus 1 times a. How about example B? Example B, let's actually consider first b squared. It's a bit different number, right? So that is 0 minus 1, 1, 0. And since it's squared, we should multiply it by itself. 0 minus 1, 1, 0. So that's equal to 0 times 0. 0 minus 1 times 1, it is -1. Second column, 0 times -1, 0, -1, 0, it is 0. Now second row, 1 times 0, 0, 0 times 1, it is 0. And 1 times -1, -1, it is 0. So here we have -1, which is equal to, it's just -1 times, what is 1, 1, 0, 0? That's our identity matrix, right? Okay. So what does it mean? It means that now if you just find, for example, b cubed, it will be equal to b times b squared, or b squared times b. What is b? B is, okay, this given matrix. Let me just write here b. And how about b squared? That is -1 times I. So this -1, I just keep this here. That's equal to -1 times b. Okay. So actually, I can just write here when it is b squared is equals -1 times I. So now it is b. So now how about b to the power of 4? B to the power of 4 is, let's say, b cubed times b. What is b cubed? That's equal to -1 times b. And here we have b. And -1 times, what is b squared? B squared is -1 times I. So that's equal to just I. Okay. So that means that what can we conclude here? That means that if this power actually is 4 is multiples of 4, right? It's always equal to I, right? If it is like 3, for example, multiples of 3, that's just equal to -b. And if this 2 is equal to -1 times 5. Okay. For example, let's say if they ask, what is b to the power of 7? So that's equal to b to the power of 4 and b cubed. This b to the power of 4 is I. What is b cubed? That's equal to minus b. So that's why it's equal to minus b times b. Right? -1 times b. Okay. The same. Actually, why did I put this? Maybe. So this one. All right. We have 3 actually slides left, and I will finish this class. Okay. So another thing is the transpose of a matrix. That's in a definition. The transpose of an m by n matrix A is the n by m matrix, and we denote this by AT in the index. That means A transpose. This is how we read this. Obtained by interchanging the rows and columns of A. That means that if you're given a matrix, we have rows, right? And just write them rows as columns and columns as rows. Then actually the new matrix is called the transpose of the matrix. Like for example, let's say if we are given what is it here? Example, let's say we are given matrix A, whose components are, let's say 1, 2, and 3, 4. What is A transpose? Also, it will be 2 by 2. Actually, it is 2 by 2. It is 2 by 3, but anyway, the rows, the column, right? The first 1, 3 is column. So you'll just write it as row. The second column, 2, 4, it becomes the rows of this matrix. Okay. So that's how we define the transpose of n by n matrix. The transpose is sometimes used to give an alternative definition of the dot product of two vectors in terms of matrix multiplication. Again, actually, once again, dot product is for vectors. Actually, for matrix, we don't have dot product, but sometimes we can just use it alternatively if we are talking about, what is it, column vector or row vector. So what is u dot v? U dot v can be written as u transpose v, right? Because if, for example, let's say vector u is u1, u2, and the vector v, let's say it is v1, v2, right? Actually here, because this one is 2 by 1, and also this one is 2 by 1, this matrix actually, if you just consider them as matrices, their product is not defined. But what is u dot v? It's just equal to u1 v1 plus u2 v2. Actually, I can just do this like this, right? It's the u1 u2 and times, here we have v1 v2. Actually, this product is defined. So what is u1 u2? It's just the column of u, right? So that means it is just u transpose, and times what is v? It's just our v. Now we are considering these vectors as matrices. This is how we change matrix product into dot product, or dot product into matrix product, if we are talking about, what is it, row or column matrices. Transpose the following matrices. A, for example, 2, 3, 1, 0, 1, 7. So this transpose is 2, 3, 1, it becomes column, 0, 1, 7 becomes column. B, for example, 9, 1, 2, 0, 4, 3, these are the columns. So if you transpose them, the columns becomes rows. So 9, 1, 2, 0, 4, 3. And also C, 3 minus 5, 2, since it's a column matrix, it becomes row matrix. That is 3, -5, and 2. The last slide, a square matrix A is symmetric if A transpose is equal to A. That is, A is equal to its own transpose. If it is so, actually, it is called symmetric matrices. That means that along the diagonal, okay, let's see here, these elements are the same. That's why it is, what is it, symmetric. And also these elements, they are the same along the diagonal, right? It's our diagonal. That's why if you just transpose, it's the same thing. Transpose of this matrix, again, it is 3, 2, 5, 2, 5, 4, 5, 4, 7. And B, if you notice here, these elements, they are the same, and also they are the same. and also the 7, right? That's why this symmetric. Symmetric means it's symmetric about the diagonal. And that's why its transpose is just itself. That means that if the transpose of the matrix is equal to itself, then it is symmetric. Now, if it is symmetric, then it is transpose must be equal to itself. Okay, guys, let's have break for 15 minutes. At 2:10, we will have our next session.